how many particles there are in the universe. We're going to calculate the number of particles in the observable universe. So that's the section of the universe that we can see where light could have reached us from. What are the particles that we're talking about here? So we're going to be interested in particles that are particles that we know exist, that are fundamental, and we're interested in the ones that have mass. So we're not really going to be talking about photons, for example. What we're going to be talking about are things like quarks, electrons, those sorts of things. So the quarks, of course, are going to live inside protons, neutrons, and the electrons are going to be in orbit around those protons and neutrons in atoms. Pretty much everything else is insignificant. So how do we do this? So we're going to use 4 bits of data. Part of it's going to be cosmological data. Data from the Planck satellite, which measures the cosmic microwave background radiation. People call it the radiation that's left over from the Big Bang. It's the radiation that you get after, when the first sort of neutral atoms began to form. So we're going to use data from that and a little bit of particle physics data as well. So these are the 4 bits of information we're going to use. So the first of these is the critical density of the universe. So this is a good measure for what is the energy density of the universe full stop. This is because we know that the universe is very close to being spatially flat. So it's not shaped like a sphere or a saddle, it's somewhere in between the two. And because of that, we know its density is very close to the critical density, which is a really, really, really light density actually. If you look at it, if you compare this to the density of water, the density of water is 1 gram per centimetre cubed. And this is a million times less than that, right? So it's super undense, right? But of course it is. This is the universe we're talking about. The next bit of information we're going to need is the fraction of that energy budget in the universe that's stored in baryons. Now, why baryons? Well, baryons, really, in this context, they're just the protons and the neutrons, which is where the quarks live. The other thing is the size of the observable universe. Again, coming from Planck data, we get this figure of about 10 to the 28 centimetres, so one with 28 zeros after it. So lots of centimetres, but the universe is big, right?
Why is it in centimetres?
Well, I put it in centimetres because this one was in centimetres and I don't want to start getting all my units messed up. So I thought it was safest to just keep one set of units in there. And the last thing that I'm going to need is the mass of the proton. The baryons that we're interested in are protons and neutrons. They've got about the same mass. They're very close. The mass is pretty much identical. And so the mass of the protons is 10 to the minus 24 grams, roughly. These are the 4 things we're going to need to work out how many particles there are in the universe. So to start off with, we're going to work out how many baryons there are in the universe, i.e. how many protons and neutrons in total there are. First thing we're going to do to calculate that is we're going to say, what is the energy density stored in baryons? So stored in protons and neutrons. Well, that's just the fraction of baryons times the overall density. This gives us the energy density stored in baryons. We want to know the total energy, so the total mass stored in the baryons. We need to multiply by the volume of the universe. But we know how big the universe is, right? It's given by this radius. So the volume is just the size of the sphere of that radius, which is 4 pi by 3, and then that radius cubed. That gives us the total energy stored in baryons. All right, these baryons, like we said, they're basically protons and neutrons, which have the same mass, essentially. So if you want to know how many baryons they are, we just divide by the mass of one baryon. Okay, so we divide by the mass of the proton. And this gives us the number of baryons. That's not what we want, no. So we want to know the number of particles. So we've got to think about how those particles are distributed. Now, one thing we know is that the universe is, on average, electrically neutral. Okay, so the number of positive charges balances the number of negative charges. For our purposes, that means the number of protons is going to balance the number of electrons. The other bit of information we can use is, we know where are these baryons stored? Well, we know that 75% of them are stored in hydrogen atoms and 25% in helium atoms. There's other atoms as well, but that's insignificant.
Not to us.
yeah, not to us, but in the broader scheme of things, it's insignificant. So by far the vast majority, so 75% in hydrogen, 25% in helium. That's where all this is stored. And we know that from looking at distant gas clouds. We also know it from one of the great triumphs of cosmology, which is nuclear synthesis. So given that information, let's suppose we took a sample of 4 atoms. Then we know that 3 of those atoms are going to be hydrogen, and 1 of them is going to be helium, right? Well, the hydrogen atom contains 1 proton and 1 electron. So these 3 contain 3 protons and 3 electrons. The helium atom contains 2 protons, 2 neutrons, and 2 electrons. So now we can split this up, because each of these protons contains 3 quarks. Each neutron contains 3 quarks. So altogether, how many particles do we get from these 4 atoms? 26 particles. How many baryons did we need to get those 26 particles? Well, we've got 3 protons, another 2 protons, and 2 neutrons. That's 7 baryons. Okay, so we get 27 particles from 7 baryons. So we know how many baryons there are in total. We know for every 7 baryons we get 26 particles. So if we want the total number of particles, we just need to multiply this number by 26 over 7. So we just plug in all the numbers, do a bit of magic, and what do you get? You get 3.28 times, and then the magic figure, 10 to the 18. So that's how many particles there are in the universe. It seems like a lot, right? 10 to the 80, that seems like 1 with 80 zeros after it. That's a big number, right? But actually, the universe is a big place. That's about 1 particle every cubic meter. Hardly anything, right? But of course, you know, most of space is empty space.
That's not even 1 atom per cubic meter, that's 1 particle.
1 particle per cubic meter, yeah, exactly. So the other cool thing to think about is you could ask, how many particles are there in a typical human body? We know the human body is about 2/3 hydrogen, about 1/4 oxygen. So from all that information, you can work out that the number of particles in a human body, about 1.46 times 10 to the 29. Okay, so that seems like a lot of particles, but of course it's not as many as there are in the entire universe, right? So how many humans would you need to use up all the particles in the entire universe? Well, of course, you just take the ratio of these two, right? So you'd need 2.25 times 10 to the 51 humans to use up all the particles in the universe. So there's about 7.5 billion humans alive today, right? The population growth rate at the moment is about 1.11% per year. So I thought it'd be fun to work out how long it would take for us to, given that rate of growth, for us to sort of use up all the particles in the universe, right? So we can work this out. If we take the population when it's using up all the particles, so i.e. this number, so this is the population, this corresponds to this number, divide it by the population now, which is about 7.5 billion, P now is 7.5 times 10 to the 9, then that's related via an exponential to the rate of growth, R, which is 1.11% per year. I can plug in all these numbers, I can rearrange this equation. I get T as 1 over R log P all over P now. So I just plug in the numbers, and it turns out that we will have used, if we carry on, the population keeps growing at the same rate, we will have used up all the particles in the universe, in humans, in 8,604 years. Which is not that much, right?
I thought it was going to be a massive
number.
I
know, it's amazing. Well, this is exponential.
Forget using up the fossil fuels, we're going to use all the particles.
Yeah, exactly. I mean, just forget what talk about impact on the planet, impact on the universe, right, of population growth. This is, within less than 10,000 years, we'll have used up, and we keep growing at the same rate, we'll have used up all the particles in the universe in the form of humans. Surely something's got to give before that happens, right?
Well, there might be only 8,604 years left for us here in the universe, but luckily that's plenty of time to learn a new skill. And a great place to learn new skills is with Skillshare. They're the sponsor of this video, and they've got something like 16,000 online video lessons to teach you all sorts of stuff, from making videos to cooking, design. And something that I'm quite keen to learn a bit more about, and that's filming with and flying drones. They've got a whole series of lessons on that, and it's something I've started looking at in a lot more depth. I got pretty inspired when we made this number file video using a drone. So finally I'm splashing out and getting one for myself. Anyway, from around $10 a month, you can get premium membership on Skillshare. You get access to all the videos, including offline, and if you're a number file viewer and you use this URL here, skill.sh/numberfile, you can get 2 free months on there. Check it all out, see what you think. One of the things that's impressed me very early on is how well made the lessons themselves are. They're really kind of professional and modern, makes them a lot more enjoyable to watch and therefore a lot easier to learn what they're teaching you. Anyway, don't take my word for it. There's that website again, school.sh/numberfile. That's so they know you came from here. And now thanks to them for supporting this video.